Okay. Well, I was thinking since I do so many videos from my room, and you can see the bird picture in the background that I painted, I figured I'd show you the other one I painted for in here. Oop, I'm moving it the wrong way. It's supposed to be like a cherry blossom tree blowing in the wind. I don't know if you can see enough of it at once to figure that out, but I just made the flowers blue since that's the accent color in my room. I don't think there really is a blue cherry blossom tree, although there should be because that would be pretty. All right. Anywho, I think we left off on this question. I'm not really sure. I had so many people walking in my house and interrupting me there during that last video. And if you hear that, it's because we have Tripod with us again. But she can't get up in the camera face at this moment. All right. Real gases deviate from ideal gas behavior at what two conditions? Okay. Remember, at high temperatures, they are flying around so fast that they can escape the attraction to each other. So at low temperatures, they can't, and that messes up PervNerd. It doesn't work as good at predicting the volumes or pressures and whatnot if it's at a low temperature or a high pressure for the same reason. The high pressure squeezes the molecules closer together, and the bigger the molecules are, the more of a difference that makes. We'll see how all this works here in a minute in terms of correcting PervNerd for these conditions. All right. Okay, this is the one we left off on. Considering the three gases, HCl at 298, hydrogen at 298, and oxygen at 350, compare the average kinetic energies of the molecules in the three samples. Well, kinetic energy is simply equal to 1/2 the mass in kilograms times the velocity in meters per second squared. So the faster they're going, the more kinetic energy they have, and also the mass matters. The more massive they are, the more kinetic energy they have. So I don't think we need additional information here because we know the temperature, which is directly proportional to the speed at which they're flying, and that determines kinetic energy, and we know their mass, which also determines kinetic energy. The heaviest gas here is HCl at 36-ish grams. The lightest, of course, is the hydrogen at 2 grams. So the heaviest gas has the highest kinetic energy, and the other average kinetic energies decrease with molar mass. Well, that's 2. Number 3 is that the HCl at 298 and the hydrogen at 298 have the same average kinetic energy, while oxygen has a lower kinetic energy. And then our last choice is the HCl at 298 and the hydrogen at 298 have the same average kinetic energy, while the oxygen at 350 has a higher average kinetic energy. That would be the correct one. Okay, the kinetic energy is directly proportional to the temperature. Okay, so we can say because hydrochloric weighs more than hydrogen, its molecules are moving slower, but they both have the same kinetic energy if they're both at the same temperature. The lighter one would be moving faster, though. And then oxygen, because it is the hottest, has the most kinetic energy. All right, would you expect helium gas to deviate from ideal gas behavior more at 100 Kelvin and 1 atm, 100 Kelvin and 5 atm, or 300 Kelvin at 2 atm? This is once again just seeing if you know when gases deviate the most from ideal gas behavior, and that is at low temperatures and high pressures. Okay, so the first one is our lowest temp and the highest pressure. Okay, that's when the helium will disobey the ideal gas law the most. So what do we do about this? We know that if you squeeze the molecules too close together and if you slow them down too much, PV will not in fact equal nRT exactly. So how do you solve that? Well, there's this lovely equation, which you're going to love typing into your calculator, called the van der Waals equation. You might recall talking about van der Waals forces in Chemistry 1. Van der Waals forces are the intermolecular forces that occur between polar molecules. They're very weak, but they are there. So we have simply added two terms to the ideal gas equation to correct for these two issues, okay? A, the fact that the molecules attract to each other, and B, the fact that the molecules do in fact have volume that can have an impact. So here's the equation. You can see how it's still PV equals nRT, okay? A simply corrects our pressure, okay, and incorporates the fact that volume has an impact on the pressure as well, because the more scrunched together the molecules are, the more that'll affect the pressure. Now, B corrects for the actual size of the gas molecules. Okay, and then it makes sense to multiply it by N, because obviously the more moles you have of the molecule, the more that's going to alter the volume, that's the free space that's available for the gases to move to. So the more molecules you have and the bigger they are, the more you have to adjust your volume. Okay? And then pressure is due to, the pressure tweaking, okay, is due to A, which is the molecules' attraction for each other. Some molecules attract each other more than others, and times the moles squared, because obviously the more moles you have, the more attraction you're going to have, divided by the volume squared. Okay, the smaller your volume, the more the molecules are going to be smushed together, and the more they're going to attract to each other, and the more that's going to mess up your pressure, essentially. I have to pause. Okay. Anywho, here is the van der Waals equation. So the correction terms A and B correct for A, the attraction between the molecules, and B, the volume of the molecules. So you need to know what A and B are both for. And then, of course, you're going to have to do the math. So this A and B, they're van der Waals constants. And there's some found in table 10.3 in your text. The van der Waals constants, A and B, there's different values depending on if you're talking about chlorine gas or hydrogen gas, so you have to know which gas you're dealing with. So here is the table you are looking for in your text. Okay, helium is a very small a, whereas carbon tetrachloride has a huge value for A. Remember, A corrects for the attraction that the molecules have for one another, okay? And van der Waals forces have to do, our London dispersion forces, maybe you've called them that. That is when nonpolar molecules will attract each other depending on the number of electrons they have. The more electrons that a molecule or an atom, has, the more that those electrons can kind of build up on one side of the molecule and make that molecule a little negative on one side, and then therefore a little positive on the other side. And then that'll cause the nearest molecule to follow suit, okay? That slightly negative side on the first, or sorry, the slightly positive side on the first molecule will cause the next molecule's electrons to kind of pull over towards the partially positive. Hold on, start this over. Okay, let's start over on this. Here's the van der Waals equation. Here are the A and B constants. For example, helium, because it doesn't have very many electrons, it cannot generate those attractive forces as well as, say, chlorine, okay, which has a heck of a lot more electrons. And those electrons can all shift to one side, making the other side partially positive, and then that can cause the next molecule's electrons to all shift to one side, and that can just have like a chain reaction on all the molecules and allow them to attract each other. And if they're attracting to each other, that's slowing them down, and they're not hitting the walls of the container as often, and so that's going to lower the pressure. So helium, because there's only 2 electrons there, it can't really do a whole lot of that kind of attraction. Whereas the larger molecules like chlorine and carbon dioxide, and of course carbon tetrachloride, those have a lot of electrons that can shift to one side, so they have a larger value for A. Now B has to do with the size of the molecules, hogging up some of that empty space in the volume of the gas. Once again, helium's very small, so it's not going to have that big of a volume correction, whereas larger molecules like carbon tetrachloride are. So it just depends on the substance how big the A and the B are. So there they are again, even larger. So when you go to do a van der Waals equation, you just need the values for A and B. So if we had 1 mole of an ideal gas confined to 22.41 liters at 0 degrees Celsius, it would have a pressure of 1 atm. How do we know that? Well, that's STP. 1 mole of any gas at STP has that volume. Okay. What we're doing in this sample problem, which I have worked out in the other video, the sample problem video, the first one, I've yet to be able to post the second one, but it does exist. Anywho, what we're going to do is use van der Waals equation to correct for that. Okay. Using plain old PV equals nRT for 1 mole of gas at STP, we'll get a pressure of exactly 1. Let's see what the pressure is going to be when we use the van der Waals equation. Okay, so here they have it arranged a little differently, but it's essentially the same thing. And we just have to look at the gas we're talking about, chlorine. Okay, so it's one of those with quite a few electrons and rather large. So its A and B values are going to be large. Don't forget, when you plug and chug into the equation, you have to square N and you have to square the volume, okay? And then, as always, try not to mess up the order of operations here. The reason this equation looks different than the other way is because they've rewritten it to solve for P and... Alright, so here it all is, and if you've done it right, go ahead and try this one in your calculator. Just see if you can type all this in and get the right answer, because how many times have you told me I'm not getting the same thing as the back of the book? And I always say something smart alecky, like, are you sure you typed it in right? And you always say yes, and about 60-70% of the time you didn't, and it was just a calculator error. So keep in mind when you're doing this, you can always check and see what the answer would be in using regular old PV equals nRT. Hey, that rhymed. But anyway, you can try it simply with PervNert, get that value, then use this ridiculous van der Waals equation, get that value, and they should be close. You shouldn't be getting like a pressure of 112 instead of a pressure of 1. Okay, it's not going to be that big of a difference. The bigger your gas molecule is, the larger your A and B values will be, and the larger your deviation from the ideal gas law will be, but it's not going to be like 300-fold, okay? So you can always tell if your answer makes sense. Using the ideal gas law, PervNert, we had a pressure of 1. Using the van der Waals equation, we get a pressure of 0.99. Okay, close, but not quite the same, and that answer makes sense. Okay, oh, and here is, this is helpful now, for your vapor pressure of water problems, if you wanted to refer back to it here. It is the water vapor pressure at different temperatures in torr. And it even goes out to the decimal place. So we will need to use this table in our gas lab that we're going to do as soon as the eudiometer tubes come in the mail. So we'll know our gas temperature out to a decimal place. So we want the most precise water vapor pressure correction that we can possibly get a hold of. And that, my dears, is the end of a very long slideshow. More sample problems worked out to come, hopefully. Wish me luck with the iPad.